Okay, forces part 1, which is really linear motion. It's all about linear accelerated motion using formulas. The easiest part, this pops up very often in section 5 and the beginning of question 6s, and occasionally you get a nice question in question 12 which also follows along these lines. A force is anything which causes a change in velocity, and anytime that velocity changes, that's called acceleration, we get a force. All of the stuff in physics, and particularly in forces, is about both things happening in different ways. A force causes an acceleration is caused by a force. They're both the same thing. Essentially, force and acceleration are two expressions of the same thing. Anytime you change velocity, you get a force, and these are measured, as you can imagine, in newtons. This is the general sort of revision slide about distance over time being speed and Dad's silly triangle. I'm not going to bore you with it. You can freeze frame at this point and work yourself through some of these questions if your mental arithmetic is slow or needs some help. What's more important is the difference between a scalar and a vector. A scalar, which can only be represented by a number. It has nothing other than a quantity, a length, an area, a volume, a time. All of these things only have sizes. They don't have anything else associated with them. They only have what we call in science magnitude. Whereas a vector has magnitude and direction. And that's why we have to represent it as an arrow. Whereas the length of the arrow gives the size, the magnitude, and the pointy bit of the arrow shows in which direction it acts. So vectors are represented by arrows to show both their size and their direction. This is a vector. The distance there, yes, that's a magnitude. But the arrow turns it into a vector, makes it what's called displacement. You have to displace yourself in that direction by 22 kilometres to arrive in Tralee, which is a nice place. Now, speed is our classic scalar. It has no direction, only a size. Whereas velocity is our classic vector. It not only has a size, as speed does, but a direction of travel. You have to say where you're going. You can't just say I'm doing 20, you have to say I'm doing 20 east, like the police do over the radio on all the terrible cop shows. Another example is mass. Mass, as you might know, is apportioned by the universe, like karma. It's literally how much matter there is inside you, and it doesn't vary no matter where you are. You can be on the moon, you can be in space, you have the same mass, but your weight changes, and weight is a vector because it always has a direction. On Earth, weight is always down because it's towards the centre of the Earth. In space, it might be in a different direction if you had any weight at all, but weight is definitely a vector. It has magnitude and direction. Here's another pair of examples. Distance, the distance between 2 points, or the distance travelled, and the displacement, what you end up further apart. The red line represents the scalar distance you travelled along the road, whereas the blue line represents the vector displacement from one place to another. Now, as we go back to this arrow, specifying a scale, giving us a good direction, showing the angle perfectly, that defines a vector very well. And this is called a vector diagram when drawn properly to scale. If you want to add vectors, if they're parallel to each other, backwards and forwards, either adding or subtracting, that's very easy. You just add them as you would normally. But if the vectors are not parallel to each other, like speed here and wind, they're at 90 degrees to each other, this is a 90-degree angle, then you have to do Pythagoras to find the answer, to find the net, the resultant, the answer vector, what actually happens. You see, this plane is flying at 120 meters per second, but the wind is blowing straight across it with 50 meters per second, and the resultant is therefore 130 down there, which we've worked out using Pythagoras, and we've worked out the angle using simple trigonometry. That's the angle here between where it thinks it's pointing the plane and where it's actually going. Now, of course, in reality, they do this calculation so the airport turns out to be here and not over here, because then they'd miss it. All of these vector additions that are done in physics are done on these Pythagoras, because we just simply don't stretch you to doing stuff with greater trigonometry. So nice, easy stuff with just Pythagoras and right-angled triangles. So it's always winds blowing across planes, or currents as you're trying to cross them, or smoke coming out of chimneys where the smoke's trying to go straight up and the wind's going straight across, that kind of thing. Everything that can be expressed at 90 degrees and put into one of these right-angled triangles. Now, if you then really get into it, you can then do calculations in the Leaving Cert. This was in 2004, quite a long time ago, I agree, but still on the present course, and it has come up again since. Notice that the numbers are exactly the same. This is because this is a Pythagorean triplet. You don't actually have to do the calculation. 5, 12 and 13 are a triplet. You should know that if you have 5 and 12 as the two sides, then 13 will be the hypotenuse. You should know. It is known, I should say. And also you can work out, again, using tangent, the angle involved. It's different here because you've been asked for a different angle, that's all. It's still essentially the same calculation. If you notice the angles, the one at this end, here and here, rather than the one we calculated in the last one, that one. Okay, so that's the one we had in the last one, so that's going to be our 23 degrees. So, you have the resultant, you have the angle, exactly the same as the last question. Now, you can also resolve vectors into two vectors. So you have one vector and you can break it into two, just like you can take two and make it into one. That's always true in physics. When you want to do this is when your vector is not acting exactly along the line you want to calculate. For instance, if you have a vector which is heading off above the ground, but you're only interested in its component along the ground, then you can simply use this. This method of doing it just breaks the vector up into its vertical and horizontal component. And this is essentially the far as we go with these calculations in physics. So a practical example might be you're trying to drag a table, you're pulling it at 50 newtons, but you're pulling it at an angle of 30 degrees to the horizontal. So the actual force you're putting on the table is 30 degrees, the cosine of 30 degrees, times the 50. So to get this quantity, because that is a right-angled triangle, what you've got, the relationship between the two is a cosine. The cosine of 30 is equal to what we don't know, what we're trying to work out, over 50. This is the 50 in the question. And so 50 times the cosine of 30 equals x, which as you can see is 43.3 newtons. So if you're looking for the force on the table in a horizontal direction, it's 43.3. Now if we needed the vertical, there it is, and that's just multiplied by sine, because that's a sine relationship between the two. Those two are the same. It's like looking at that one on the far side of the rectangle. Another problem from even further ago, this one, 2002, something's being pulled. What's the horizontal and vertical components? Again, you're just multiplying by cosine to get the one which runs along the ground, and by sine to get the one which goes up vertically. Very simple questions, always done in exactly the same way. But the basic idea is that you can break a vector down into its parts, and that makes it easier to use, and you want the bit which is going in the direction you're interested in. So a better example still is this question from 2003. He was obviously busy in the early 2000s with these questions, wasn't he? I mean, he really stuck at them for a while. This is all to do with if you're trying to walk up a hill. This gentleman's in a wheelchair. He's wheelchairing up a hill. If you're trying to go up a hill, the steeper the hill, the greater the force against you. Why? Because the greater the angle. You see, as you're looking at the angle, you're multiplying by the cosine of, in this case, 10 degrees. Well, the cosine of 10 degrees will give you this value here, the weight straight down. But the sine will give you this value, 156. Now, as the angle of the slope increases, of course, so does the sine of the angle increase. And that means you've got a greater force. So if this is equal to the sine, as you can see, the sine of 10 degrees, if you had 20 degrees, you'd have a greater figure there, more than 156, and that would make it more difficult to go up the slope. So this is physics predicting what actually happens. And it's all about working out components. Now, this is a particularly difficult one. You might not challenge yourself with this in the exam unless you were doing applied maths. But the idea of breaking into components so you get the part of the force which is important to you, that's what I'm trying to get at here. So summarise any vector broken into two parts. The horizontal one is times the cosine, the vertical times the sine. Okay, acceleration again. I am not going to trouble you with this. You can freeze the frame here and just work them through mentally if it's any help to you. But I expect most of you will understand that acceleration is a change in velocity over time. So you literally subtract the difference between what you're doing now and what you were doing, and you divide it by the time it takes you to change. And that gives you the acceleration, mathematical acceleration here. Acceleration is also a vector and is also represented by an arrow. Okay, so at junior set, you probably did distance time graphs. Well, these are velocity time graphs where we put velocity against time instead of just distance. And so they represent different things. For instance, here, the second one, that shows that the thing is moving at constant velocity, i.e. its velocity is not changing. It goes along at 40 kilometers an hour, or whatever it is, there, constantly. This one shows linear acceleration. So the acceleration is a constant number. In this case, the slope of it, maybe it's 2. So that gives us a slope of 2 meters per second squared. Deceleration is represented by a line going down because the velocity is decreasing. And again, this is constant deceleration because it's a straight line. We can maybe this acceleration would be 4 meters per second squared. Now, the per second squared is the difference of acceleration to velocity. Velocity, of course, is meters per second. Meters per second squared is the unit for acceleration because you're essentially dividing by time twice. Velocity is distance over time and acceleration is velocity over time. So you've divided twice by time, and that's why you square the seconds there. Okay, this is a general graph showing it all together in a sort of journey. First you accelerate, then you travel at constant speed, then you accelerate again, and finally you decelerate down to your destination. Now, why do we draw these graphs? Well, it's very easy to represent a journey. Here is some easy questions. How fast was the object going after 10 seconds? 10 seconds was going at 40 meters per second. Okay, what is the acceleration from 20 to 30? Okay, this is 20, this is 30. Okay, it's gone up by 20. It's increased by 20 in 10 seconds. So the acceleration is 2 meters per second squared. And you can work your way through those questions if they interest you at all. But the real beauty is that we can divide the area under the graph into sections, find its area in terms of the units on the axes, not in terms of the number of squares, but in terms of the distance on the bottom times the velocity going up the y-axis. We can find those distances and they will give us the area travelled by the object during this period of its transit. So here, as I've done it out, let's consider first the easiest section, the square in the middle. The total velocity along the side there, that distance, is 40. It goes from 0 to 40, it's 40. The distance along there, well, that's 20 seconds, from 10 to 30. So that's 20 seconds. So we multiply the 40 by the 20 and get 800. And that's 800 meters travelled. Now, if we find the area of the others, some of them in triangles, we need the half there for the triangle. There, there. We find those three triangles, we find those three areas in terms of meters, add them all together, and we find that the thing has travelled 1,700 meters or 1.7 kilometers during the transit. And that's the beauty of the velocity time graph. As well as doing it by graphs, we can also do it simply by formula. These formulas, as you know, all in the logbook. None of them you have to remember. And all you have to do is write down the information that you've got from the question and then find the appropriate formula. A car starts from rest. That's it, rest. There we are. Then u is equal to 0. A is equal to 2. There we are. That's A being equal to 2. And T is equal to 12. We write this information down and we're looking for the final velocity, which is V. So we look for a formula which combines them all and we find this one. We do that for each of the questions. That's the way you do it. You write the information down with the letters. You write down the formula because you get the 3 marks. And then you substitute the numbers in and calculate the answer. This is simple stuff. You have got to be able to sub into formulas. Here's another example, even simpler in some ways. A train accelerates from rest. Again, remember, rest means u is equal to 0. At 10 meters per second squared, well, the squared tells you it's an acceleration. For 12 seconds, well, that can only be a time. So you put those numbers, you find the formula, how distance it's travelled, S, you want S. You look up the, there we are, that's the one you find, that's it. And off you go. Now, there are some proofs. Here's an example of a proof. If you want to start with a formula. Now, we're trying to prove this formula. We're trying to get to this formula. Not from here, obviously. That's not where we're starting, but that's what we're trying to prove. And we always start with the other formulas. Now, there's the 3 I've already mentioned, but there's another one which usually is the one we use for almost all of the proofs. So we'd usually start with u plus at. That's the simplest of the formula. But the one we kind of need, which perhaps doesn't sound like an important one, is that it's dead silly triangle, to be honest. That one is the other one in this case, because we're trying to replace t. Let me show you how it works. So we have v equals u plus at and t equals distance over time. Well, distance in this formula is s. Speed, well, the speed, of course, in this case is the average speed. There's a starting and an end speed. So we have v plus u over 2. Now we can rewrite that. The 2, which is at the bottom of the bottom, goes up to the top. So we end up with t equals 2s over v plus u. And that's what we replace the t up here with. I'm going to change colour to try and make it easier. So now we have v equals u plus a times 2s over v plus u. Now, and here's where the clever part comes, at least it's clever to me. I move the u over to the other side. I then take this v plus u and it goes from the bottom on this side to the top on the other side. And that equals 2as. There we have the difference of 2 squares. V squared minus u squared equals 2as. So v squared equals u squared plus 2as. And that's the solution. Usually put a square box to show we've done it. Okay, so that's the whole question. Now, Obviously that's not for everybody, but that's the proof of the formula, and I hope that's not too bad. I think you can kind of work it out as long as you remember that when you're using the formula, that's your speed, v plus u over 2, the average speed. Okay, this is the standard experiment done. You can do it with a motion sensor, you can do it without. This is velocity and acceleration experiment. In this case, we're looking at the time it takes for the card to pass between the light beam and then the distance of the card, which is L, divided by the t gives us our velocity. So the velocity u from this section, there, that u is the L length of the card over t1, and the velocity v, the final velocity from that section, is L divided by t2. We also have to work out the distance between the two beams, so we can use the formula v squared equals u squared plus 2as to work out a. And when we have A, we can use the forces, which is the number of weights you put on here, to work out, to draw a graph of F against A, and the graph of F against A will come out as a straight line because it's Newton's second law you're proving here. And the only other thing to note is if you take a weight from here, it's meant to be stuck onto here, so that the mass during the experiment remains constant. You have to keep the mass constant. So you don't just remove a weight, you remove it and you put it onto there, usually with a bit of blue tack to make it stick on. This is the question I'm going to set you for this section, slightly longer than most of the other ones I'm going to set you. And as it's early on, some of this stuff you may have to look up. I don't see any problem with this. It's quite an important question. Note sometimes not very many marks are given, in which case there's probably a one-word answer. Remember, there's two types of motion in physics, constant velocity and simple harmonic motion. Does this look like simple harmonic motion to you? And if it doesn't, well, the answer should be obvious. I'm hoping it's all obvious. I'm getting on to part 2.